Okay, ELE 115. I'm looking at week 7, unit 16, RL parallel circuits. You thought RL series circuits were enough, but no, we've got to do parallel. So, I'm going to take the circuit that's in the discussion in the Cengage material, and I'm going to go through it step by step. One of the things that we want to remember with parallel circuits, there's one voltage. It's just between these two nodes here. This node and this node. That voltage between there is always going to be 240 volts RMS, 0 degrees, and this is a 60 hertz problem. So, parallel circuit, one voltage. So V total is equal to VR is equal to VL. Multiple currents, there's a current through the resistor, a current through the inductor, and when they add up, they give you the total current. Now, a lot of these things require vector addition. Sometimes they don't. So we'll try to be mindful of that as we go through. So the current through the resistor, we just use our Ohm's law formula, V over R. Again, the book uses E, and E and V can be interchanged, but modern app notes and everything use the V. And so even though I was taught with E back in the day, V is more popular and is seen more in industry publications. So V total is 240 volts at 0 degrees, and the resistor is 15 ohms at 0 degrees. So the current through that, doing the division, is 16 amps RMS. And I should say, when people specify something as 240 volts AC, if they don't say anything else, they really must be referring to RMS. And even though on oscilloscopes we like to use peak to peak because you can see it, meters like your digital multimeters, where they have an AC volt scale, they are measuring RMS. So if you if you measure this AC voltage, from this node up here to this node down here with a multimeter set to AC volts, you would measure 240 volts because that's RMS. And remember, RMS, we have all these terms. RMS is the heat producing equivalent. In other words, for as far as dissipating power, if we could put 20 12-volt batteries in series here, we'd have 240 volts DC. That would burn as much power in this resistor as 240 volts RMS, which is really like 240 volts RMS is really like, from 300 plus 338 volts peak to minus 338 volts minus peak. So that peak to peak voltage is like 676 volts peak to peak. Okay. So here we go. Again, it's Ohm's law. IR equals the total voltage across that resistor, divided by R, and we come up with 16 amps RMS. The voltage is 0 degrees, resistors are at 0 degrees, and so that current is at 0 degrees. The current through the inductor, however, we have 240 volts RMS at 0 degrees, divided by 20 ohms, and in this problem they give you X sub L. You don't have to compute it. They give you X sub L, and that's 20 ohms, and of course inductive reactance, if you want to look at I'm going to go down here. If you want to look at a reactance calculation, inductive reactance is always at plus 90 degrees because it sticks straight up. The resistor is at 0 degrees. That's the x-axis, if you will. So we have 20 ohms at 90 degrees. So when we do the division, 2 into 24 is 12. The zeros cancel. 12 amps RMS at minus 90, because 0 minus positive 90 is negative 90. So our current through the inductor is at minus 90 degrees, and the voltage across the inductor is the same as V total, is at 0 degrees. So true to form, the current in the inductor lags the voltage across the inductor by 90 degrees. All right. Now the real power, P sub R here, or however you want to call it, it's equal to, there's no real power dissipated in a pure inductor. And so you can find the real power simply by multiplying the voltage across the resistor by the current through the resistor. And when we do that, we get 240 volts RMS at 0 degrees times 16 amps RMS at 0 degrees, and we wind up with 3,840 watts of real power. Okay. Now the reactive power, the volt amperes reactive, is equal to the voltage across the inductor times the current through the inductor. And the funny thing about it is, it will always be, depending on the type of circuit, at plus or minus 90 degrees, because it's reactive. And so the voltage at 0 and the current at minus 90, this will be at minus 90, but we really don't care. We've got that covered in the term volts amp reactive. So we can just multiply 240 volts RMS by 12 amps RMS, understanding that they're 90 degrees out of phase, and that's what makes this power reactive. So we have 2880, 2880 or 2880 volt amps reactive. Now it might be a good time to figure out the inductance of this thing here. We know that inductive reactance equals 2 pi FL. We know XL, they gave it to us, it's 20 ohms, and that's equal to 2 pi F. F is 60 hertz, and L is a variable. So we can, just work this equation backwards, and we find that L is equal to 20 divided by 377, which comes out to be 53.1 millihenries, or 0.0531 henries. This is actually a more proper representation, but either of these is good. Now, we know that I total is equal to the current through the resistor plus the current through the inductor. So if we add these together, it's going to have to be a vector sum because they're at different angles. So the current through the inductor is at minus 90 degrees, and that's because we divided 0 by positive 90, gave us negative 90. The current through the resistor, of course, is at 0. So we have to do a little vector sum here, and we have to take 16 squared plus 12 squared, the square root. And this is essentially 3 times 4 and 4 times 4. So this is a 3, 4, 5 triangle, and 5 times 4 is 20 amps. And if you don't believe me, just do the whole thing out. You'll get 256 plus 144, which will give you 400. Take square root of 400, you get 20 amps. So the magnitude, and that's what this absolute value notation here says, the magnitude of the total current is 20 amps. Now we have to find its phase angle. Well, the angle of the current is going to be the angle whose tangent it has an opposite over an adjacent. Remember, tangent equals opposite over adjacent. So I need to find the angle whose tangent is minus 12 divided by 16. Minus 12 is our opposite of this angle right here. And 16 is the adjacent of this angle right here. So you maybe more properly call this angle theta sub I because it's the angle for the current. And we get theta equals a tangent to the minus 1. That's the angle whose tangent is negative IL over IR, and that is approximately 36.9 degrees. And that's typical of a 3-4-5 right triangle, by the way. So now we go down here. Yeah, so in a parallel circuit, we had to add these two. We had to take a vector sum of those two currents to get the total current. And now we come down here and we look at a typo right here. This should actually be ZT equals VT over IT. So I will try to rescan this and get this cleaned up for you. But yeah, this should be VT over IT. And sorry about that. And you can see here I have V and I have I. So I don't know why I wrote R here. This is VT over IT. That's Ohm's law. All right. This would be great for calculating the current, but I'm calculating this one, so this guy should be current right here. This RT is IT. 20 volts RMS, 240 volts RMS at 0 degrees divided by 20 amps RMS at minus 36.9 degrees. Well, 2 into 24 is 12, and the zeros cancel, so it's 12 ohms, and the angle is at 0 minus a negative 36.9, so Z total equals 12 ohms at plus 36.9 degrees. And it should be plus because this is an inductive circuit. I mean, it may be a parallel circuit, but it's still an inductive circuit. So the impedance should be at a positive angle because, you know, you think about it, the inductive reactance sticks up, R sticks out, the resultant vector has to be, you know, at some angle here. Okay. Let's find the total impedance by another method. Let's put Z total, okay, as a combination of R in parallel with XL. Now, because we have two things, I'm using this product over the sum formula. You could do 1 over R, 1 over the quantity, 1 over R plus 1 over XL. But I'm doing the product over the sum, which works for two entities in parallel. And the R is 15 ohms at 0 degrees times 20 ohms at 90 degrees. That gives you 300 at 90, because 0 plus 90 is 90. And then on the bottom, we have a vector sum situation that we need to take care of. Okay? So this is to find the denominator of this thing. So we have to add these, you know, in a vector form. And that would look like XL would be 20, R would be 15. Again, we've got a 3-4-5 triangle because this is 3 times 5, that's 4 times 5. The answer must be 5 times 5 or 25 ohms. And when we run the calculations, we find that to be true. It's 25 ohms. I'm sorry, it's 25. This is a denominator now. It's 25. I guess it would be ohms. And we'd be at an angle whose tangent is XL over R, you know, opposite over adjacent. And so this would be 25 ohms at 53.1 degrees. And Z total, now we have to take what we had in the top here, 300 at 90, divided by what our denominator was, 25 at 53.1, and you divide this in here. If you had $3, you'd have 12 quarters, right? There's 25 there. So you have 12 ohms at 90 degrees minus 53.1 degrees is 12 ohms at 36.9 degrees. And that's exactly what we calculated up here. I just wanted to do two methods to show you that you get the same thing. All the rules apply. So let's look at apparent power. Well, apparent power, you just multiply the magnitude of the total voltage times the magnitude of the total current. You don't even care about the phase angle. All right, and when you multiply 240 volts RMS by 20 amps RMS, because our total current, let's go back up here, our total current came out to be 20 amps at 36.9 degrees, okay? But the magnitude of that current is 20 amps. So I come down here to volt amperes, or apparent power, and I multiply 240 times 20, and I get 4,800 volt amperes. Okay. Well, you could say 4.8 kilovolt amperes. That's probably, technically a better way to say it. So let's do a check here. Does VA squared equal PR squared plus VAR squared? Because in the Cengage material, they said the apparent power was like the hypotenuse, okay? And the real power and the reactive power were like the two sides of the right triangle. So in a right triangle, the hypotenuse squared is equal to the sum of the squares of the other two sides. And when you do this all out, you will find, yes, that expression holds. So that's a good check. Now, power factor, you can find a number of different ways, and I'm taking these ways from the Cengage material. And again, I really should have, on some of these, I should have absolute value or magnitude type things. The power factor is equal to the magnitude of IR divided by the magnitude of IT. It's 16 over 20 gives you 0.8. You multiply it by 100 for percent, and you get 80%. The other way to look at it is, now this is a parallel circuit. Oops, sorry. So it's Z over R. In a series circuit, it was R over Z. But Z over R, 12 over 15, again, it's 0.8. Multiplied by 100, you get 80%. And here's another one. Power factor is the real power over the apparent power. So that's 3840 over 4800. It's 0.8. Multiplied by 100, you guessed it, 80%. And one other way is to take the power factor of the impedance angle, or current angle, I guess, either one. So we have a cosine of minus 36.9 degrees on the current. That's equal to 0.8. Multiply it by 100 to get 80%. So you get a lot of validation there. So I will post this document, but I will make this fix right here, as this should be IT. All right. I thank you, and that should help you with Week 8, Unit 18. Okay. Later, people.